Hi everyone, this is part 2 of section 5.3 on the fundamental calculus theorem. So now we want to do some examples of this. What we have from the fundamental calculus theorem is essentially that if we can find the antiderivative of certain integrals or the certain functions, then we can use them to find the value of definite functions or definite integrals and find the area that is given by certain curves. So let's see the first example here. We have 3 square root of x dx. And so notice that for this we can use the antiderivative. We can think of this as 3 times x to the 1/2 dx. And this is going to be 3 times x to the 1/2 plus 1 over 1/2 plus 1. Using the rules of the derivative, plus c, or 3 times x to the 3/2 divided 3/2 plus c, or again this will be 6 over 3, so that's equivalent to 2x to the 3/2 plus c. And we can think of this as the function big F of x, the antiderivative. So that means that if we are considering 4 to 16 of 3 square root of x dx, by fundamental calculus theorem, we can think of this as f of 16 minus f of 4. And that's going to be twice 16 to the 3/2 plus c minus twice 4 to the 3/2 plus c. Simplifying these values, we're going to have that this is 2, and the square root of 16 is 4, so 4 to the 3, right, plus c, and minus, and then square root of 4 is 2, and then 2 to the 3 is 8. Just playing around with the exponents here to simplify the values. Now 4 to the 3 is going to be 64, so this is going to be 128 minus 16. Notice that c is going to get canceled with this other c. And now this is going to be equals to 112. So that's the first example. Now let's do a shorter one with example B. We have the integral of 3 sine of x dx is just going to be minus 3 cosine of x plus c. Okay, since the derivative of sine is cosine, and the derivative of cosine is minus sine, then the antiderivative of 3 sine dx is going to be minus 3 cosine plus c in this case. Now, since that happens, the integral from 0 to 2 pi of 3 sine of x can be considered the antiderivative here. I'm going to call this g of x. You can call this g of 2 pi minus g of 0, or just minus 3 cosine of 2 pi, and then plus 3 cosine of 0. Both in these two cases, this is going to be 1. This is also 1, so this is going to produce a 0 for this integral. And now for the last example, we have the integral from square root of t minus 1 divided by t dt. Doing the antiderivative of this is equivalent to just doing t to the 1/2 divided by t minus 1 over t dt. And this is going to have, this can translate to t to the minus 1/2 minus 1 over t dt. Now, if we find the antiderivative here, this is going to be t to the minus 1/2 plus 1 over minus 1/2 plus 1 minus log of t plus a constant. Or the simplification of this will be twice t to the 1/2. Okay, and this is what we can call our antiderivative f of t. Now we're interested in the values 1/16 to 1/4. So now we can talk about the integral from 1/16 to 1/4 of square root of t minus 1/t. And so this is essentially f of 1/4 minus f of 1/16. And that means twice 1/4 here minus, and at this point you start to see that we're always going to lose the constant. So every time that I'm going to do in the future these calculations, I'm just going to lose the plus c value immediately. So now this is just square root of 1/4 is 1/2, so 2 times 1/2 minus, and we'll lose c with c. Square root of 1/16 is 1/4, so 2 times 1/4. So this is equivalent to 1 minus 1/2, and it's just going to be 1/2. Okay. So now this is the end of the basic examples of whatever we can do with the fundamental calculus theorem. Of course, if we take a look at this and we resolve the results geometrically, we can think of this as having a positive area, and in this we're going to have a negative area and a positive area that they're going to cancel each other, and so that's why the integral is 0. And in this case, similarly, we're going to have a positive area. You can verify this by actually graphing each of these functions and seeing the results that we get. And so in the third part, we're going to see how this can be applied in more general cases and for limits of integration that have functions.